Okay, well, hello everybody, and thanks to GSNI for inviting us to give this webinar. We're really excited to be able to present to you all. In the main, we're going to be talking about the Geothermal Campus project that we have going on campus. And we'll also talk a little bit about the work we're doing on the sort of go beyond the scope of the campus project as well. So before we do that, I'm going to take a little step back and just think about why geothermal is important and why we need to be looking at it, particularly in the UK. So just taking these two images here, so looking at the one on the left-hand side is of UK emissions in 2019, so the carbon emissions. And we're going to really focus on the pink bit, which is a substantial part, 30% of the amount of UK emissions in 2019, of which is sort of the carbon emissions for buildings, of which 23% of the total is heat, and a substantial proportion of that. So almost a fifth of our carbon emissions in the UK are down to our homes and heating our homes. So if we move over to the figure on the right-hand side, you see in 2020, our UK residential heating systems were predominantly 86%, in fact, heated by gas boilers, and therefore the reason why we have so many carbon emissions from our heat. So an obvious way of dealing with that is to electrify it, to move onto things like air source heat pumps and electro boilers. And the reason for that, if we look at this next slide, on the left-hand side, our electricity grid is doing pretty well, actually, for decarbonisation, and we'll move into a sort of almost completely decarbonised grid at some point in the not too distant future. And so it offers a really good solution for decarbonising our buildings, to just simply move from being gas heated to maybe putting in a great big electro boiler that provides the same heat but without the carbon intensity. We've got the electricity grid, so a lot of organisations, including University of Leeds, is looking at an increased electrification process for decarbonising, and because it's an easy solution to put something like an electro boiler in, and it effectively decarbonises your business. But the problem that we have with heat is that heat is seasonal, and as I'm sure most of us have been doing over the last couple of months, we put our heat on in the evening, and everyone's doing it at the same time because it's cold. And the problem with the grid is that the grid doesn't have that sort of capacity. And if we all decarbonise at the rate we're planning to decarbonise at over the next 5 or 10 years, if everybody goes down that route, our grid quite simply won't be able to cope with it, particularly in the urban environment. And that's where geothermal comes in. It's not the solution, it's a help to the solution. So, you know, if it can provide 10-20% of the heat needs, then it takes that load off the electricity grid. So let's just take a quick look at what we're looking at from an aquifers point of view. So there's quite a lot of different solutions for geothermal in the subsurface, and I'm sure you've had lots of presentations that look at lots of different options. So what we're focusing on really at Leeds at the moment for our project is aquifer controlled geothermal. And when you look at UK geothermal potential, many of the maps that you see around what sort of potential we have are focused very much on the principal aquifers. There's a number of reasons for focusing on the big principal aquifers in our subsurface. One is if they're deeper. Big, deep aquifers, then they provide higher temperatures. So it allows us to look at maybe having temperatures of 30-40 degrees rather than very shallow aquifers that give us 12, 13, 14, 15 degrees. They're large aquifers, so they're hundreds of meters thick, so when you drill down to them, you've got less risk involved. You have a better idea of where they are because you've got a much bigger depth. So if you drill and you're slightly out in your estimation of where they sit, you've still got a good chance of hitting them, whereas a smaller aquifer, it's less certain. And they're potentially also more easily imaged in seismic data because they're a really big aquifer. They potentially offer a better reflective surface. That's dependent on the materials. So the risk for these sort of deeper aquifers in particular is the high drilling cost. So if you're looking at something, so for example, underneath Leeds, our aquifer sits at below a kilometre's depth. You're looking at much higher drilling costs to actually get down to that depth. And with that also comes a bigger uncertainty understanding our fracture connectivity at that depth and how productive the reservoir is actually going to be. If you're looking at outcrops, for example, to try and understand your fracture networks, do those fracture networks at the surface in outcrops, are they still reflected down a kilometre depth? What does it mean to have greater overburden, for example, on that sort of fracture how open the fractures are and how connected they are? So there's a lot more risk in actually whether the reservoir is going to work in any sort of long-term way. So that brings us on to looking at aquifers that are really sort of overlooked in the national story, when we're looking at much smaller aquifers, but actually they give scope. So for somewhere like Leeds, where our major aquifer is much deeper, actually looking at minor aquifers could be a very viable option, particularly if they're less than 500 metres. The drilling costs are a lot less for much shallower aquifers. And again, they're not the whole solution, but can they be part of an integral geothermal solution where we look at all the options down to the sort of like the deeper 1.5 K early Carboniferous limestone below Leeds, but also looking at a lot of those much shallower aquifers. So, for example, underneath Leeds, we have a number of sandstone aquifers, 40-50 metres thick, such as the Ellen flags, the rough rock intervals, or sitting in these sort of middle and lower coal measures, that sit sort of 60 to 250 metres below the whole of the sort of urban environment of the city of Leeds. And they offer a lot of potential for Leeds without having to drill to the much deeper principal aquifers. And that's what we're focused on in our Geothermal Campus project. So that moves smoothly on to talking about the project. So the project itself was an investment by the University of Leeds to firstly sort of explore the potential for geothermal energy on campus, but also in recognition that it's essential that we refocus both our research but also our teaching into the energy transition, and the university was looking to support us being able to do that as well. So it meant that we not only drilled a couple of wells to see if we got some good fluid flow, but actually we drilled a number of test sites that allow us to monitor and have permanent equipment and to extract core, etc., that will allow us actually to do really full set of research on the aquifer that sits beneath us. So our team is a multidisciplinary team, and it's a really lovely environment to work with all these sort of different inputs into geothermal energy. So the actual project team consists of 2 PDRA. So ARCA will be talking to you all shortly, and so ARCA is very much focused on the geoscience side of the work we're looking at. And there's also David Barnes, who is a social scientist and has a very strong background in working in local government and indeed heat networks in London and in the London district. And he brings a really interesting very political and governance side to the work we're doing. We also had a research assistant, Joe Kelly, who's now nicely converted to a PhD and still working a lot with us on sort of the thermal side of the reservoir, understanding about the thermal heat flows in the reservoir below campus. From an academic point of view, there's geoscientists, myself, Nick Shaw, Richard Collier are those sort of ones working actually with the project, but behind us there's a whole swathe of geoscientists in our department from lots of different fields who are feeding into the work we're doing as well. We also have engineers, so Fleur Loveridge and Simon Rees, looking at the sort of above ground systems as well as sort of the engineered side of drilling beneath campus. And then we have social scientists Jamie Van Alstyne and Finn Bale working with us as well. So just having a look at the starting place that we had for the university commissioned a feasibility study for a number of solutions on campus. So looking at comparing air source heat pump solutions with closed loop systems and open loop systems. And they also commissioned some studies, excuse me, of energy use on campus, really understanding how the energy was used, what sort of energy use for each of the buildings, and sort of breaking it down into where we might have energy centres to bring different types of energy solutions together. So if you look at the image on the right-hand side, hopefully you can see there's some purple lines that sort of make a network of lines across campus. And at the bottom, Jay, can you see my mouse? My mouse is moving around. The GSC down at the bottom, this red box here, actually the hospital LGI sits here as well. And this generating steam complex sits between the two. And effectively for the university, that complex creates steam that is then pushed through this sort of purple network of pipes all the way across campus. So if you've not been to Leeds University campus, it's effectively the size of a small town. And that steam, you can imagine, as it gets further across campus, is extremely energy inefficient. So the university is aiming to sort of take parts of campus off of the steam complex network and putting it into some sort of alternative decarbonised solution. So on the left-hand side, if you see there's like red boxes around campus that have increased in number and location, which delineate energy centres across campus. And each of those energy centres can have a different solution. So it may be that one area is better suited to air source heat pumps only, or electro boilers, or geothermal only, or closed loop, open loop. So we're exploring all those options across campus, and it means that we've got quite a lot of flexibility in having diverse solutions across campus. So from a campus project view, I'm not going to talk you through all of this because it's quite a text-heavy, laborious slide, but it just shows that we've got three stages really that we've been working to. And the first stage was very much the working with external engineering companies, working with estates and the university to sort of explore the potential for geothermal and moving towards putting it out to tender. We didn't really have an understanding of whether we were going to be drilling or not at the start of the project, but that moved quite quickly into a phase where we were really supporting the actual drilling process as a whole as well. So our first sort of year and a half was very, very hectic and very focused on drilling the test sites, advising and helping support where those test sites would be, etc. We've now moved into stage 2 where we have all the data and we're working very much with getting that out to everybody, trying to understand what we got from the data and analysing it and producing results. And in part, we moved into stage 3 where we're looking at sort of really applying what we're learning from campus to larger strategies. We do quite a lot of work with Leeds City Council that I'll come back to later. And then up at the top right-hand side, do you know there's potential to apply the same processes to other aquifers, and there's other work that's going on in our team looking at the carboniferous limestone as well. So really quickly before Arca takes over, I'm just going to talk about how we fed in as geoscientists into the decision-making process. So once the feasibility study came back, as per sort of, I'm sure many of these sort of initial engineering oriented feasibility studies, the model of subsurface campus was you know, reasonably simplistic in that it gave an estimate of what was going on under the surface. And what we were able to bring as a team was to actually take a lot of our legacy data, so BGS sort of structural fault maps, lots of borehole data, and any data that we could get hands on basically. So you can see in the cross section below, that was a cross section of a model that we built of beneath campus. You can see it's quite faulted beneath campus, so we have quite a lot of questions about potential compartmentalization and whether there's compartmentalization at all. So understanding how our reservoirs beneath campus might work together. So if you can see my mouse, this sort of area here is beneath campus. You can see we had a number of boreholes, a slightly deeper one beneath the School of Earth and Environment that was drilled about 14 years ago. And we also struck lucky going into town, a much deeper one, which allowed us to evidence that the rough rock was actually down to around 200 to 250 metres depth. That allowed us to convince the university that actually it was worth drilling to investigate that area as well. So using this cross section, we were able to sort of find an area. What we really wanted was an area that actually wasn't impacted by a fault. So we chose this. So this area here sits near the engineering cluster, and we chose to drill one of the test sites in this area here, and that meant that we were able to look at the aquifer without a fault going through it, because we wanted to understand how the aquifer behaved itself. And we also drilled in this location here with the aim of actually potentially cutting through a fault, so we could look at fault damage zones and understand how those faults might impact fluid flow in the reservoirs. So very quickly to talk you through the test sites. So this area on the map, it shows the campus as a whole, and you can see sort of all these sort of closed loop, open loop sort of crosses at the top end of the campus. That's up by what we call the engineering cluster, and the aim was for these sites to actually both test what potential we had, but potentially join it into the engineering cluster energy system, because so that it could be taken offline from the steam network. So our setup in the test site, actually I'll go on to the next slide because we talked through on that. You can see on this map as well at the bottom end, so this is actually down by the School of Earth and Environment. We have another pilot well. So these two pilot wells, they're actually wells that we got full 250 metres of core from. So we have 500 plus metres of core. We also had full geophysics taken down both of the pilot wells, and we have permanently installed optical fibre DAS DTS cables in both of the pilot wells. We also have a number of closed loop wells, and they had full thermal response testing, and again are permanently kitted out with DTS cables and the opportunity for us to do more thermal response testing with our thermal response testing rig. So test site one, it looks pretty much like this. So if we're looking at trying to understand the reservoir, you can see the open loop wells sit here, and they're on either side. We have our closed loop sort of monitoring wells for monitoring sort of thermal changes. So if we start to extract from open loop well 1, we can monitor the thermal plume if we're re-injecting into well 2 with either cold or with hot water from the high energy, high HPC computing center. We can re-inject heat, and we can monitor how that heat plume behaves, for example. And we also have the pilot wells very close by as well. So it creates a system where we can actually actively monitor and do work with the reservoir. Test site 2, sorry, I should just go back. So we intended to have one pilot well, but because of an engineering faux pas, we ended up with 2 pilot wells, which as scientists we're never going to complain about. And what we've actually designed it now is so that we actually monitor one reservoir. So you can see it's blocked in after 150 metres and allows us to monitor the Allen Flags Reservoir. And the pilot well 2 is only slotted casing down by the rough rock aquifer. So it allows us to look at the 2 different aquifers in isolation. Our other test sites, so we've got a closed loop by the Storm Jameson halls, and the reason we have that closed loop site is because we're potentially looking at those halls being used, having a closed loop system supplying heat to the halls of residence. And then we have the open pilot well down by our school that allows us to do testing. We already have MSc and undergraduate projects taking place. One, for example, is using the DAS, which is is acoustic, so you can effectively do a vertical seismic profile of the well, and we've got a student who's been doing a project working on that. Very quickly, because I've absolutely no idea what time it is now. I'm just going to talk about some of the work we did whilst we were waiting for the wells to be drilled, and sort of data to start becoming available to us. We knew that we had a number of questions that we really wanted to focus on. One was how compartmentalized is the subsurface, understanding what sort of fluid flow we have. Also understanding what sort of damage zones we have around the faults in our aquifer, and how extensive that damage zone is, and also what the background noise effectively of the Allen Flags fracture network. So what is just there in situ in the Allen Flags, regardless of whether there's faults or not. So we explored the sort of wider West Yorkshire area where the Allen Flags outcrops, and we found a number of quarries which ticked a lot of those boxes. So we had a quarry that has a fault right through it. We have a quarry that sits near to a major fault with some minor faults in it. And we also have a quarry that has no faults near it at all. So it has allowed us to explore what those fracture networks look like in the outcrops. I think Ark is going to talk about these more, so I'm not going to get into this, but this is an example of one of the quarries, and we're working on publishing this information shortly. I think, is that me? No, the last one. So just as a way of handing over to Arka, the geoscience, I'm going to come back to the social science after Ark has finished talking, but the geoscience side of things is very much Arka's focus on, so starting with legacy data and the static model that we built for the university to be able to make decision making and good decision making, as it turns out. We're moving on to sort of bringing those models. So we're looking at field data, bringing in the core well data, and then creating a dynamic model and iteratively modeling it going forward as we get more data from using the actual geothermal reservoir. At that point, I'll hand over to Arka.
Right, so it seems that 3 is the magic number for splitting modeling work down into. So again, essentially, the geoscience modeling can be split down into 3 stages as well. And not to belabor a point, it's essentially a consequence of the timing of the different things that happened on campus and access to the data. Again, as Emma pointed out, I've just got a blowout of the site locations, and you can see that we made the conscious decision to locate our doublet system essentially on one side of the fault, because the exact nature of the fault, whether it was open or closed, or indeed the orientation of the fault itself, that was an unknown. So because we didn't have that constraint, we wanted to sort of work around it. And a large part of the modeling is essentially to try and get constraint for all of these and sort of parameters where we don't know what exactly is happening. And that's what stages 2 and 3 are meant to do. But as you can imagine, there's loads of assumptions that were made at the early stage of the project. So again, like Emma said, the best thing to do is if we can break it down into the key questions. Like she said, there was a borehole that was drilled on site before. From that, we did know that the system's got loads of fractures in it, and that's likely to be where the flow is coming from. But still, we want to get a handle on essentially how much flow we can get, what the nature of the fracturing is, how open or closed they are, and what implications that might have on, say, if we were to use the system as an ATES, for example. Also, in terms of forward modeling for the ground source heat pump, what implications that would have. And then again, like I said before, whether the faults are sealing, is there compartmentalization within our sort of aquifer itself? So, you know, we have to dust off our field boots. And that's where stage 2 comes in. And again, the field analogs, like Emma said, really simply, structurally, all the units are dipping to the southeast, so it was just a case of going up dip to look for exposures. And so we had these 4 active quarries. And over here, this image is really to give you a sense of the scale in terms of getting exposures where essentially we've got the interwell spacing for our doublet. So we can start using it as a really good proxy for what the Ellen flags, the aquifer itself, will do when we look at it in the field. And what we see is essentially that, you know, from a sort of architectural point of view, you can see stacked channels, for example. But the bit that I'd like to draw your attention to, and I think you can sort of see in, well, this overcast image of the same one from before, is that you can see these sort of thick mudstone interbeds in between. And these are important because they're the ones that, while we were out there, what you tend to see is that pond sort of to the bottom left of the image, that's sort of the water's pooling on top of another one of those mudstone interbeds. So clearly that's having an impact in terms of how the fluid is flowing through this entire aquifer, and you see that along the sides. You also see mechanically it's having an impact in terms of the fracturing and jointing, because we find that they tend to be strata bound, so you get terminations against these mudstone interbeds, and that obviously has a compartmentalization implication when you think about it in terms of modeling. And then on the side, we have some of the sort of other work that was done. So you can see a rose diagram just giving you the primary, the 2 main sets of jointing that we see. Again, there's no surprises here. The bulk of the jointing follows the sort of predominant fault trends in the area. You can see that we've been trying to do fracture tracing as well to get an idea of how much sort of fracture porosity and fracture permeability we'll get, because again, these are flagstones used for building. What we found is that and what I'll show in the very next slide is that they're very tight sandstones. So again, we're really reliant on the fractures, and therefore getting a handle on them is crucial. And then, of course, we've got some sedimentological logs as well done in the field. As Emma said, the 3 sites were picked in terms of essentially to give us an idea of how the fracture networks vary based on their distance from a fault. And if you look at the graph on the right, again, it's pretty obvious. What we see is, again, no surprises. You get an increasing percentage of fractures the closer you get to a fault. So again, everything's staying consistent with the assumptions that we had made in stage 1. And they're all useful model parameters. So like your porosities and permeabilities and whatnot. But again, I should caution that using the parameters that we gain from our field proxies, we have to be careful because the sort of confinement, the stress regime that we see in the quarries is obviously going to be very different to that we see on campus, because we're at the top of the hill where the drill sites are. So that's something to keep in mind. Here, again, I said earlier, the sandstone was super tight. If you can believe it, these are stained thin sections, but there's very little blue dye, which again, it's consistent with what we were expecting in terms of there being very minimal matrix porosity, and it's all in the range of 1%, 1 to 2% and under, which isn't that much of a worry, because what we find that there's still a significant amount of fracturing and jointing, and that is going to allow fluid flow. But again, it's good to confirm it at the sort of grain scale as well. Here we can see on the left essentially what that stage 1 sort of pre-drill model would have looked like based off of the legacy data sets. And then what we can then start to do is basically incorporate that into some of the forward modeling that we do for the aquifer. So over here, this is one of the early stage 2 models. I nickname it the Duplo model. It's a really simple 2-layer approximation of our system. And you're starting to see basically how we're starting to be able to model how the plume would behave based on different configurations of our doublets, because they're reversible. We can play around with which one we have as our injector and producer and what impact that has on the plume. In these particular screenshots shown over here, I should add that they're static models, so they're not taking into account parameters like groundwater flow. So obviously you get a nice donut-shaped plume as a result. Quick shout out to Sequent and Volsung for access to the software for this part of the modeling. And again, just to close off some of the stage 1 stuff. So while drilling was happening, we could use that stage 1 sort of model to essentially do well prognosis. And then in real time, as the drilling was happening, we could correlate our sort of expected results against what, say, in this example, the chippings that were coming in, or our fractured intervals. Could we relate that in terms of the zones where we had flush loss, for example, or core recovery percentages? So yeah, you can start to see that, you know, you're forming a picture where things are linking up to one another. So now on to stage 3. This is essentially where now drilling completes, sort of summer 2024. So we're starting to get access to all of that drilling data. What can we do with that? What sort of nuance can, and what sort of additional parameters can we introduce into the modeling? So that's essentially the post-drill phase. And here it's just a snapshot of all the drilling data per se. So you've got an absolute smorgasbord. You've got wireline data. We've got our image logs taken in the pilot wells. So you've got your acoustic image, you've got televiewer data. And then, as Emma said, there's shed loads of core. Is more than the 500 meters that was planned because of the sort of fortuitous additional drilling that needed to be done. And then we've got the pump tests as well. So you've got your constant rate tests, step tests, etc. Then there's also the thermal response testing data. Now, if any alarm bells are ringing because of the really high thermal conductivities there, that's essentially a sign of fluid flow in the area, which is resulting in those, well, spuriously high thermal conductivities that we see here. But that, again, links into some of the work that we're trying to do with using fiber optic DTS in conjunction with TRT rigs to sort of constrain those effective thermal conductivities along the sort of aquifer section. For those who know about the coal in the area, I thought I'd show just a couple of examples. So there is some history of coal in the area, but there's no major coal seams around the campus region. Possibly there's the Better Bed coal seam. And in fact, if we look at the bottom left in the driller's log, they do make note of a thin band of coal. And sure enough, when we look at our core images, you can see that coal, again, it's reflected in our image log data. And then again, you see that in finally, once the geophysical data comes through, you see the characteristic low gamma, low density resistivity spikes and neutron porosity spikes exactly where that coal seam is. So it's all starting to tie in really well together. Again, an example of the amount of core data that we have. We know that, well, we can say that's the densest data set we have simply by weight. But if I can draw your attention to some of the images, you can see that there's loads of fractures through the core as well. And you can start to see that some of the cores have staining, sort of reddish iron staining around the fractures, which again is confirming what we hoped in terms of them acting as conduits for fluid flow. So again, it's all about layering and building up our picture of the campus subsurface. So next up, in terms of those fractures, what we can see is I've just got a section over here where I want to highlight how we can start to map those fractures across. So you see the fracture in the core, then you've got our sort of 3D core visualization, and then, you know, using our image log data, you can start mapping those fractures. So over here in the blue, you've got that fracture plane, you've got the sinusoid, and then below that in the green, you've got what we've interpreted to be a bedding plane, for example. And then you can see again on the right-hand side how that would look in the wireline. Again, a quick caveat to add is that in this process, we're also sort of QCing our depths. So we do see that there is a difference between the core box depths and what we have in our wireline, for example. So that's, again, part of making sure that the data sets are all sort of fitting in together. And then finally, so some of the ongoing work. So on the left, you can see some of the sedimentological logging that's being done for, we're trying to do as much of the full core as possible. So we've just about completed the entire Ellen Flags aquifer, logging that. Then you can start seeing with the image logs, we're starting to log the structures in there as well, in terms of the fractures. In terms of the core as well, additional work that is pending, is ongoing, is scanning it. So CT scanning the core segments themselves, taking plugs for analysis, so for thermal conductivity tests, mercury pycnometry tests, and whatnot. There's also the wireline log analysis. And then, of course, there's a bunch of tests that we want to do using the wells on campus. So there's the embedded fiber optics. So we've got DAS and DTS cables. So we've got the DAS, DTS, we've got our own TRT rig, so we want to do thermal response testing as well. And then we've also used some data loggers kindly loaned to us by the University of Mines for time series data for pressure and temperature within our pilot wells, so we can get a record of the change in the water levels, the temperature change in the water over time. And then you know, in terms of additional work, there's obviously further reservoir modeling to be done. And then in terms of field work as well, there is a option where, you know, we've collected the drone data for photogrammetry that could be worked up into discrete fracture network models. So essentially now it's taking all of that data and sort of feeding it into sort of cohesive stories and getting the papers out. So yeah, there's a lot to do, and I'm gonna hand off to Emma on that note.
Yeah, so thanks, Arka. Yeah, just to finish off, I'll talk through just a few things and particularly focus on what other work we're doing. But just to add, sort of a lot of the work that Arka's doing, there's a lot of really detailed work, but we all have a sort of collective aim, and that's really to try and understand how we can use what we're doing on campus. Firstly, to guide the university. Obviously there's a big campus and the test site is a small area, to really sort of try and project that across campus and try and understand how we can help make the university make the best decision making. And I'm going to come back to that from a social science point of view in a minute. And the second sort of aim, and it's a much bigger aim, I guess, is really to try and understand from the data that we have and the sort of really sort of complete data set that we have, to try and understand how we can use that to help de-risk and de-cost future exploration for everybody else in the UK when they're looking at shallow aquifers. So understanding how we can look at, for example, comparing core and data in core that ARC is working on at the moment, and looking at the geophys and understanding what's the minimum amount we can use for that to, you know, to reasonably get good models and to be able to sort of de-risk drilling for those different aquifers. So there's a lot of focus for us to try and make our test site much more useful than just for the university. So just sort of taking a step back and looking at from a social science point of view, because obviously David's not here to present his work, but I think it's really important that we recognise that as geoscientists, and I don't know the audience on today, I'm sure there's quite a lot of geoscientists, but the thing is with geoscience, the geoscience of the subsurface in the UK, we're pretty good at it as a community in the UK. There's lots and lots of geoscientists who not only work in the UK, but work around the rest of the world and have huge amounts of experience. And so, you know, we have that covered sort of. We've got loads of questions we have to answer about it, but it's something we do quite well. And actually, what we really need are other people to be involved, because we can geoscience the death out of everything. But if we can't get other people to understand the opportunity to change legislation and all of those other aspects, then we might as well not do anything. And so we've really learned to and really sort of embraced the fact that we need other people to support us getting geothermal on the agenda. So just looking at it from David's, so our social scientist point of view, David Barnes, we've sort of put together this map, and really to focus on the two. So you've got the sort of starting point, and I've been informed that niche is an actual term. So we're understanding that we have at the moment geothermal in the UK is niche. It's not overtaken by the mainstream. We're not taking it up in a big way, and that currently it's in an environment that is considered to be niche from a social science point of view. And David's task is to bring it from niche to mainstream. So understanding what he needs to ask, what he needs to solve, what he needs to understand to get to the other end in the big blue circle, where we're providing clear pathways to enable change. And in a slightly smaller blue circle, the effective alignment of national and local policy planning and funding strategies. So David's job, not just across the Geothermal Campus project, but a number of other projects that we're currently working on and worked on in the last year or so, is really starting to identify how to create those pathways and actually help local government and national government decision-making and support those decision-making. So I'm not going to read through all of this, but it's really interesting. It's a really interesting process to observe, and for us as geoscientists to understand how important this aspect is. So, for instance, just going along the top, you know, understanding who the key decision makers are and how they can support change, what we need to give them, what data we need to give them. So when it comes from a geoscience point of view, it's always just a number. What sort of energy is in place? Where does it sit? How can we plan it? Do you know what levels of planning are we? Can we have a multifaceted view of the subsurface? How should we be planning that? Do you know all those questions we need to answer? And then people like David take that to the people who can make decisions to use it. So that's the sort of work that David and the other social scientists on the team are working with us on. So just some quick words about the other work that we're doing. So we're obviously out on the lookout for where we can use the on-campus lab to benefit obviously the wider city of Leeds, Yorkshire. 6 million people live in Yorkshire, so if we can help make change in Yorkshire, that's you know, a big tranche of the UK population, but also looking at the UK and the wider international community to understand how we can use our campus lab to help with collaborative research. Two examples of that work, we had 2 projects funded last year, so we finished it last October, that were Research England Policy Fund projects, and both were working in conjunction with Leeds City Council and DESNES. And again, it was our team all working together. We got an additional 2 postdocs to help with the research, and one was focused on so there's 2 aspects. So Leeds has a district heat network called Leeds Pipes. It's currently heated by something called a RERF, which effectively burns it burns Leeds waste, and it creates electricity from burning the waste, but it also has heat as a byproduct. That heat is put into the Leeds Pipes network, which comes all the way into the city and heats a whole bunch of council buildings and council flats and a whole load of other businesses as well. So the first project was to look at how we could change that energy supply to a clean energy supply, such as geothermal energy, how we could actually also support growing that Leeds Pipes network as well with geothermal energy. The second project was looking at understanding, so Leeds City has been part of the government's network pilot heat network zoning pilot programme, where we were looking at where best in the city would be best suited to have a heat network, a district heat network. So we've taken a number of those zones for heat networks around Leeds, and we've assessed their geothermal potential in the subsurface alongside what's happening on the surface, the likelihood of being able to use a geothermal within a heat network. Both of those projects entailed us doing a full 3D model down to about 1.5K in the subsurface beneath Leeds, to effectively provide numbers, again, to provide data to allow us to be able to produce reports that you can see on the left, the reports that the council can use as evidence of how they could use geothermal in these networks. And the second sort of set of work that we're doing, we've just started an Ofgem SIF project that we're calling GeoGrid, and this is using the University of Leeds campus, so all its sort of projected electrification data and buildings data and the geothermal living lab as a test environment to try and understand whether and how well geothermal could be used to offset the need for increasing electrification in the environment. So going back to that very first slides I showed you, where we talked about the problem with the overextending of the electricity grid. So we're looking at ways that we could reduce that overextension of the grid by offsetting with geothermal energy. So instead of putting in air source heat pumps and electro boilers, we'd be using geothermal as part of the solution. And the other aspect that we're looking at is to try and understand, so currently we pay billions to curtail renewable electricity generation in the summer, and actually potentially using that curtailed electricity to heat water to put back into those geothermal systems and recharge them over the summer and use them as a form of long-term energy storage. So they're examples of projects that we're working on and looking to collaborate on. Before we finish, just a bit of a shout out, because we've talked extensively about the Geothermal Campus team, which is a small group of us, but I really need to make a shout out for the much, much bigger Geothermal Leeds research group, which is currently an interdisciplinary team of around 30 academic staff and growing, and all the postdocs and PhD students that come with that. So it's a really big body of people here at Leeds working on everything. So obviously geosciences and the engineering side, but from an engineering point of view, there's people working on corrosion and system optimization. So looking at understanding the energy system on the surface, all the way through to people in the School of Earth and Environment who deal with things like energy poverty and vertical farming and all sorts of stuff. So it's a really thriving environment, and we're really open to understand how we can collaborate with people and work with people to help further geothermal. And I think that's it from us. Thank you very much for listening.